Good afternoon. My name is Rrezarta Krasniqi, and today I will be presenting a paper automatically capturing quality-related concerns in bug report descriptions for efficient bug triaging. So you might wonder, who cares about quality? And what we mean in this context, we mean about quality of the software in terms of issues related to non-functional requirements, significantly important code, quality attributes, and so on. And to that, we can say that not only developers care about it, but also management team, because of the cost saving and the financial planning that is needed. The architectural and design team, especially for when it comes to defining the right architectures and the planning overall for the system development. The development team for implementing the application, and finally the quality assurance testing team, which focus mostly on test cases and achieving user acceptance. Now, we might also ask the bigger question, why do we care about detecting quality bugs, for example? Well, to that, there are several reasons. One of them is the loss of business, the loss of user interest, loss of credibility, and loss of functionalities. And just to give you an overview of just a real example, live example, the iOS system have recently upgraded one of the operating systems of the one of the iPhone's updates, and from what we can see here, there are a lot of issues that concerns quality issues. For example, at the very beginning we see that they are bringing some performance improvements, and then we notice that they also adding new features to help share the photos on the phone, and then we again have performance issues that they are improving, and then finally they are also providing some privacy features to protect the phone on the web being tracked. And the same thing applies also to the Mac itself. One of the recent updates shows that pretty much most of the updates done to the system relate to portability, security, usability, and so on. And even in this example, we can see obviously there are issues with security, or like, let's say, usability concerns that relate to, I don't know, so play music to play on the multiple AirPlay 2 speakers and so on. So now going to the real problem. So obviously those were examples of bug fixes, but let's look at the real examples of two bugs. Specifically, if we examine the Derby 5552 bug, we can, after reading this short description, we can tell that the problem relates to performance concerns, mainly because the three keywords that are shown here, the deadlock, the timeout, and the hanging, are good indicators expressing a performance concern. This is a very short description, but if we look into deep dive into the overall bug report, we notice that we have to spend quite a lot of time to understand what's the bug about, and even in what relation we need to tackle the problem. Similarly, the Derby 853 bug is also referring to the reliability concern. And this can be seen from these two words, inconsistent in value. Obviously, the method returns inconsistent value, which in a way brings concern on the reliability of the results. So we are focusing on these two. We just focus on those two problems, and even me just mentioning them took time to elaborate. But what happened is that in real world problems, there are multiple bugs being reported daily, and there are too many to deal with, and they're time consuming, and even if there is someone involved in triaging them, it takes time to who to triage it to, who is more equipped to handling certain bugs or quality bugs or security bugs or performance bugs. So just an example, the Mozilla developers, for example, said that every day almost 300 bugs appear that need triaging. So this is far too much for anyone to handle. So here comes our solution. We present here a machine learning algorithm, specifically a 3-feature selection technique that we use to detect automatically the content, or based on the content of the bug description, we determine the tagging or the labeling of the quality that it belongs to. So to achieve that, we provide 3 methods: the chi-square feature selection technique, the mutual information, the extra trees. The first one, the chi-square feature selection technique, is basically a statistical method that it assesses the goodness of fit between features and the classification. And the outcome is that it compares the size of any discrepancies between the expected results and the actual results. So for each bug report, we count the frequency of each word and create a vector based on the raw frequency value. Similarly, for the mutual information, the difference is that it provides a co-occurrence, or at least it detects the co-occurrence patterns of terms in text to reveal hidden textual semantics in that context. And the outcome is similar to what we presented on the first one. Similarly, the action is that we present here a vector approach, a based approach. And then the extra trees creates fully randomized trees, having a structure independent of the output values of the training samples. So even here, the outcome and the action are almost similar to the previous 2 approaches. Now let's look at the overall architecture of our design. It consists of 3 parts, and each of the 3 parts we are going to discuss in the next slide. In the following slide, we can see that we have 4 components, and on the first one, we download the 6 open source dataset, which belong from 2 large open source systems like Jira and Bugzilla. Then we implement an XML parser, which is supposed to extract the important metadata from each of the bug reports. Then we store such information into a plain CSV file with all features, bug ID, bug description, and so on. And then we apply the standard information retrieval text preprocessing steps for each bug report, such as tokenization, normalization, stop word, and stemming. And this is important because it ensures that any noise in the text or in the data is removed before any training and testing takes place from the classifiers that we will apply. Next, we show the 4 components of the classifiers, and those are the chi-square method, mutual information, and extra tree. So first of all, before that, we have to apply the TF-IDF model so that we can compute the weights of each of the keywords and each bug report. And then we use the chi-square, mutual information, and extra tree so that we can extract only the most significant keywords from the text. And that's pretty much it. And then we would start on the 3rd part of the classifier, which is really the training and evaluation. We construct a classifier. We apply SMOTE technique to even out distribution of all classes, because we not only have the non-functional requirements detected, but also the functional ones. So if we look at the ratio between these type of bugs, so usually there are more functional or behavioral bugs than there are non-functional ones. So we had to apply SMOTE so that we can balance the classes. And then next once we take a new bug report, we then use the classifier to evaluate the 20% of instances of the bug report from step 10, and then we determine the label by picking the one that is the highest probability. And finally, the classifier returns the type that the bug report belongs to, and we can see that down here depending on the keywords that are picked by either of the three algorithms, then the bug report description is tagged as or labeled as either performance, maintainability, usability, and so on. So let's look into the research questions. So we present three research questions. The first one focuses on the quality type variation. So we ask a question: how well do our feature selection models perform when we classify bug reports by specific quality types? The second one, we wanted to know the overall performance of our classifier. So we ask a question: how well do our feature selection models perform overall across all quality types? And the third question, we ask: what are the most informative features that contribute toward improving prediction accuracy of our classifiers? Basically, this focuses on the feature importance. So, but before we dive into the evaluation or the results or the numbers, we have looked at the quality concerns based on the taxonomy provided by ISO standard and the FIRST model. These are the 6 projects that have been taken from Bugzilla and Jira, which were also used by other previous researchers. We have focused on 5,400 bug reports because it was recently, we have these 5,400 bug reports from 6 different projects have been manually labeled in our previous paper in 2021. So we just used the label data for this new project, and we started with the evaluation process by comparing our approach, or comparing 3 different techniques with a baseline. The baseline that we used was the TF-IDF, but then we wanted to see that just using TF-IDF was not enough to produce or to generate good results. And so for that reason, we wanted to boost the algorithm itself, so we tried combining TF-IDF with mutual information, with chi-square method, and then the extra tree method. And then we compared the results, which one did the best. So now that we showed how the evaluation was performed, we here show the results. As you can see, our results were primarily done well based on the combination or configuration of using random forest plus TF-IDF and chi-square. And specifically, we noticed that our approach has done really well on detecting performance, reliability, maintainability, and even security-related bugs. It has not done very well on the functional bugs, but we will explain on the discussion on this matter. So let's look at the results of each of the configurations. As you see, we have shown the results for the TF-IDF, then TF-IDF and chi-square, and mutual information and extra tree. And from all 4 approaches, TF-IDF and the random forest with chi-square method was the winner. And overall, the accuracy of our classifier was a precision of 76%, the recall of 70, and the F1 of 58. And we also show the confusion matrix because obviously there were some false positives and negatives, but overall this just shows in which situation our algorithm did best and which ones it didn't do much better. Obviously you can see for the functional requirements it did not perform as well because there are many false negatives. Now, going back to the research question 3, it was important to know what are the features that were considered more significant for the classifier to use them as indicators for tagging certain bugs as quality ones. And this is a list of, we just here provided the top 15, but obviously if we look at certain keywords, like let's say on the performance, bug overflow large, verified timeout, minute, lock, out of memory, CPU, slow, deadlock, leak, hang are all indicator keywords for expressing concerns related to performance. Now, discussing our findings. we noticed that the combination of predicate and argument seemed to distinguish the quality-related information. We also noticed that discriminating keywords not necessarily work for all types of bugs, primarily because some of the bugs were not easily discerned by specific keywords. So this happens usually because functional bugs were often intertwined with the quality bugs. And for example, software developers would use specific refactoring terms inadequately to address behavior errors in the code. And so this, in a way, so maintenance issues were kind of, or maintainability issues were kind of intertwined with the functional related concerns, which being able to make this delineation through the classifier was difficult to achieve, which means that we would have to have another more advanced kind of AI-based technique to be able to detect such information. There are, of course, some threats to validity to point out. For example, the open source system that we use were from Jira and Bugzilla, so we haven't used any projects that are more like towards industry based, but they were quite large enough so that they could be generalizable. And then one of the internal threats is the class imbalance, because of course if the data is not balanced, then the machine learning algorithm would not perform as well. But we handle this by using the smoke technique. And then the classification algorithm, which is the construct thread, we chose the ones that were we chose this 5 ML algorithm from a benchmark study done previously by other researchers. And then we still have some work to be done in this area. So in the future, we want to determine the context of quality keywords from the classifier as part of the post-processing step. We want to enhance the classifier with supporting functionality to form a clear-cut distinction between quality-related bugs and functional bugs. So our goal is primarily to incorporate ontological guidelines for differentiating these two types of classes. And we want to incorporate NLP-based solution and knowledge-based topology to detect cross-conflicting quality dependencies that potentially can cause system degradation. And with this, I conclude our talk. If you have any question, I would be more than happy to answer them. Thank you.